Okay, today we study Newton's method. Three topics. First, I present the formula for the Newton's method. Then the second topic, Newton's method can be derived from Taylor's theorem. And then second three, I want to show Newton's method is a method of order 2. Bisection method is a method of order 1. Newton's method is order 2. We still consider a single equation. Yeah, single equation. In the second part of 3.2, we will study Newton's method for a system of equations, but now still single equations. Let me plot the graph of function f. Of course, I assume function f is continuous. In practice, in some cases, it is difficult to know whether the function is continuous. But anyway, let me assume f continuous. And in this diagram, this equation has one root, say arrow here, root, one root here. Now I want to find this root. How? Take a point close to arrow, say take a point close to arrow. Correspondingly, there is a point on the graph of the function f. This point is x0 function value at x0 because this point is on the graph of the function. So y coordinate is function value. Now, at this point, draw a tangent line. Draw a tangent line. Then the tangent line will intersect x-axis and a point. At a point, right? At a point. Graphically, this point is closer to the root arrow. We call this point x1. X1. Okay. Okay, then at the point x1, we draw a tangent line to the graph. The tangent line will intersect x-axis at a point. The point, let me call it x2. Yeah, and so on. At x2, draw a tangent line, then we get x3. Yeah, x0, x1, x2, x3, and so on. These points are called the points obtained by Newton's method. Newton's method. Okay. Yeah. Okay, now let me derive the formula for the points. Let me draw a second diagram. X-axis and then y-axis. Function. Okay, now suppose the graph of the function is this. This is the root that we want to find. Now, this point, suppose the point sk. Now, at sk, there is a point on the graph corresponding to xk. This point is xk f of xk. Now at the point, draw a tangent line. And the intersection point with x-axis is considered to be xk plus 1. Now I want to determine xk plus 1. The slope of the tangent line is derivative of the function at xk. This is slope. Now by point slope formula, I can write down the equation of this tangent line. Point slope formula: y minus y1. Now y1 is the y coordinate of this point. It's equal to slope derivative at xk times x minus x1. Now x1 is xk. Yeah. So from here we get the equation of the tangent line is this. I want to determine the intersection, the x-intercept of the tangent line. So set y to 0 and solve this equation for x. So here, a solve for x, then we get negative f of xk is equal to derivative at xk. Okay. Then move derivative to the left side and move xk to the left side. Then we get the y-intercept of the red line is minus f xk x. Yeah. Graphically, we can see that xk plus 1 is closer to the root arrow than xk. And consider the intersection point is an x coordinate as the next step of Newton's method. So Newton's method is the following formula: xk plus 1 is equal to xk minus f xk derivative. Yeah, this formula, this is a iterative formula, right? Starting with some point x0. Then step by step, we get a sequence of points. Though the sequence approaches the root arrow. Yeah. Yeah. This formula is Newton's method. Okay. Now let me present an algorithm to implement Newton's method. Yeah. Algorithm. Okay, let me copy Newton's method. Okay. The method is here. Algorithm. Yeah. Step 1. First, input initial guess about the root x0, and input a positive integer m. We want to run Newton's method a maximum of m steps. We don't want to run the method forever. Okay. Delta, a small positive number, and epsilon, also a small positive number. Okay, now step 2. Evaluate function value at x0. Evaluate function value at x0, then store the function value in variable v. Okay. Step 3. If the function value in absolute value less than epsilon, if the function value is small enough, then we consider x0 is the root arrow. Then stop. Yeah. Okay, now otherwise, for k going from 1 to m, m is the maximum number of iterations. Okay, now we have x0. Now let me use this formula to compute x1. So x0 by this formula minus function value at x0, it is a v, then over derivative at x0. This is x1. Now store the value in x1. Okay. Now x1 is a new approximation to the root arrow. Evaluate function value at x1, then store it in u, in v. Okay. So the old value in v is overwritten in v. Okay, now if absolute value of v is small enough, then we consider x1 to be the root. Or x1, yeah, the current approximation to the root arrow minus x0. x0 is the approximation in the previous step. If the current approximation and the previous approximation are close enough, we also stop and consider x1 to be the root arrow. Then stop. Otherwise, if none of these two conditions is matched, then continue. Okay, then repeat this formula, or repeat these 2 steps. Actually, repeat these 2 steps. Now, x1, store x1 in x0, then repeat this 9 and this 9, and also this 9, these 3 9s. Okay, then put an n, and this n, and the for root, and the for root, and the for root. Yeah, this is an algorithm to implement Newton's method. All right. Now let me present one example. Say example about this algorithm. Example. Yeah, take a look at one example. Say example 1. Use the Newton's method to find the negative zero of this equation. R tangent x is equal to 0. Now the function f is the left side. The left side is function f. Function f. Okay, I use this algorithm. In MATLAB, write the algorithm in MATLAB and then run the algorithm. Okay. Now the solution is let me make a table. K is the number of iterations. This is xk, not x0, xk. Xk, and then function value at xk. Initially, when k is 0, the initial approximation I choose -7. We are looking for, according to the problem, we are looking for the negative root, -7 first. Then function value at -7 is -0.702 times 10 -1. All right, now the first iteration of Newton's method, then I get -10.67709 and so on. Function value is 226, 10 to -1. Iteration 2, I got -13.27916 and so on. Function value -0.437, 10 to -2. The third step, -14.05365. Function value 0.239, 10 to the third. Now, after the 3 iterations, Newton's method is speeding up very quickly. 4, -14, 10, 11, and then here is a -0.800 times -6, 10 to -6. And then 5, -14.10126. Function value 11. See, very fast. And then the next iteration, 14.10126. Function value 10 to -20. In fact, Newton's method is a quadratic method. The convergence rate is quadratic, much faster than bisection method. Yeah. This formula is Newton's method. This formula can be obtained from Taylor's field. This is a topic 2. Yeah, topic 2. We derive Newton's method by Taylor's field. Okay. Topic 2. Newton's method by Taylor's field. Okay. Suppose we have computed xk. Now we want to get xk plus 1. And then xk is only an approximation to the root arrow. And then arrow, the root that we want to find, minus xk, denote this difference by h. Now, I use Taylor's theorem to estimate h. Okay. So, of course, from this equation, we have, if I move xk to the left side, then the true root is equal to xk plus h. Now, I want to obtain h. Okay, I use Taylor's theorem, so I need to make some assumption about function f. Assume function f is in C2, AB, okay, where AB is an interval containing the root arrow. Okay, now I apply Taylor's theorem. Okay, now f sk plus h. Actually, this is the root arrow. I expand f of sk plus h by Taylor's theorem. Sk plus h, f derivative at sk, and then plus error term 1 over 2 factorial f second derivative evaluate at some point psi times h squared. Okay, where psi is a point. It's a point between sk and sk plus h. Sk plus h is arrow. So psi is a point between sk and arrow. Okay, now from here we get f arrow is equal to f sk plus h f, then plus but I assume arrow is a root of this equation. So therefore, function value at arrow is 0. Then again, 0. am doing is try to estimate h. Now let me drop this term from this equation. Then again, 0 roughly is this. This is a f, not h. F. And now solve this approximation equation for h. Then again, h roughly to be negative f xk, then divided by f derivative xk. So therefore, from this equation, therefore, the root, yes, it is equal to sk plus h. Roughly, it is sk. Let me plug in this quantity in h. Roughly is this. Roughly is this. Now, I consider this as xk plus 1. Xk plus 1 should be closer to 0 than sk. Then we get the Newton's formula. The Newton's formula. Yeah. So Newton's formula. Newton method. It is sk plus 1 is equal to sk minus f. Yeah. We can obtain Newton's method from Taylor's theorem. Let me, about Newton's method, let me make a remark. Okay, a remark. Newton's method, yes, very fast, but in practice, there are many drawbacks about this method. The first one is if the starting approximation is not close enough to a root. Actually, in practice, we don't know where the root is. So actually, we don't know, okay, how close h0 is to the root. If x0 is far from the root, the Newton's method may fail to converge. Any example? Easy to pick one example. Say, take a look at this example. Yeah. Take a look. Okay. 0 here. All right. This function quite special. Okay. Now the root is here. I want to find arrow. If I pick initial guess here, say for example here, okay, then x1 is the intersection point of the tangent line at x0 with the x-axis. Let me draw tangent line. Yeah, okay. Now draw attention line. Draw attention line. Then x1 is here. Now to get x2, draw attention line. Draw attention line. Then this point is x2. To get x3, draw attention line at this point. Let me use green color. Okay, draw attention line. Draw attention line. The tangent line intersect x-axis and a point very far from arrow. So if the function look like this, and if x0 is chosen to be not close enough to the root arrow, Newton's method doesn't converge. In practice, we don't know root arrow. Of course, we don't know how close x0 to arrow is, right? One drawback. The second drawback is the Newton formula is this. A big drawback is this method requires derivative of the function f. In many cases, in the real world computation, function usually is given by a finite number of function values, not a continuous function. Right? From some experiments, we connect data, a finite number of data points. So in most applications, we don't know the formula for function f. How can we compute derivative of the function? A big drawback. Okay. Yeah. Drawback is need derivative. Yeah, this is a big drawback. Therefore, Newton's method is a theoretically is a method in theory, theoretical method, not a practical method. Newton's method. But anyway, it is very fast. Even though x0 should be close enough to the root arrow, but there are some special cases where you can arbitrarily choose arrow. Newton's method is guaranteed to converge. Yeah, let me present one of these cases. Take a look. The function. Theorem. In this theorem presents one case where initial guess x0 can be arbitrarily picked. If function f is in this set, second derivative x6 and continuous, and domain is the whole wheel line arrow. Okay. If function f is increasing from calculus, that means that derivative greater than 0, increasing everywhere greater than 0. And concave up, yeah, concave arm. Okay, this is a concave arm, and this is concave down. Okay, and concave arm. In other words, second derivative greater than 0. And also we assume the function f has 0. Function f has a 0. Or in other words, this equation has a root. Okay, a root. Same meaning. Okay, now conclusion is in this special case. Conclusion is then the 0 is unique. That means that the function has only one 0. And the Newton's iteration, Newton's method, the Newton's iteration will converge to this 0 from any starting approximation, starting point, x0. If you draw a diagram, very easy to understand this theorem. Say, let me draw, okay? Say a diagram here. The function is increasing and concave arm and has a 0. So the graph increasing concave arm. Yeah. There is a root here. Arbitrary pick a point, x0. Then draw tangent line. This is x1. Then at x1, draw a tangent line. We get x2. At x2, draw a tangent line, we get x3. It is guaranteed that the points x1, x0, x1, x2, x3, x4 converge to the root arrow. Guaranteed. In this special case. This is topic 2. Now the third topic. Error analysis. In this topic, I want to solve Newton's method. The convergence rate is order 2. Topic 3. Topic 3. Okay. Newton's method is, let me write down the equation because I need it, is equal to xk minus function xk f xk. Okay. Now I assume, okay, xk is approaching to some root arrow. Okay. Now I want to solve. I want to solve this convergence is order 2. That means that by definition, limit k approaches infinity, xk minus arrow absolute value over xk plus 1 over xk minus arrow approach some number. This number, non-zero number, of course, greater than 0. Not necessary to be less than 1. I want to solve this limit. Okay, now first let EK, E means error, is the distance of xk from R. Okay, not the distance. Distance has absolute value, but no absolute value here. Okay, okay. So this limit, the top is absolute value of, the top is EK plus 1 absolute value, and the bottom is absolute value EK. Okay. All right, now let me determine EK plus 1. Okay, EK plus 1 is xk plus 1 minus R. What is xk from here? Now I plug in the right side in the xk here. Then I get xk minus f xk over minus R. Xk minus R is EK. Then derivative at xk. So common denominator, then I get EK times F derivative xk minus F xk, then over derivative xk. Okay, now let me apply Taylor's theorem to the numerator. Okay. By Taylor's theorem, theorem or Taylor's expansion, Taylor's theorem. Okay. Taylor's theorem. We have f xk minus ek. Now I expand this function value. It is f xk minus ek f derivative xk, then plus error term ek square times f second derivative evaluate at some point psi. Okay, where psi is a point between this number and this number. Okay, between xk and xk minus e. Xk minus e. What is xk minus e from here? This is I get arrow. I move arrow to the left side, ek to the right side, then I get sk minus e. Yeah. It turns out that sk minus e is arrow. So psi is a point between sk and arrow. Okay. Yeah. Yeah. This number is arrow, but function value at arrow is 0 because I assume arrow is the 0 point of the function. Okay, so then from here we get, function value is 0 is equal to f xk minus ek derivative, then plus 1/2 ek f. I'm sorry. Here, quadratic convergence. Here, the denominator should be, the power should be square. Yeah, square. So here is absolute value of ek square. Yeah. actually, you see, denominator, yeah, actually, the first two terms is the numerator, but the sign is opposite. Okay, now let me move the first two terms to the left side. Then I get EK F XK minus F XK is equal to 1 over 2 factorial EK square F sine. Okay, now I plug in this equation into the numerator. Then I get EK plus 1 is equal to this. Okay, so I get EK plus 1 is equal to, go back, I forgot, is equal to 1/2 EK squared. 1 EK squared F second derivative sine, then over, yeah, numerator, then over F derivative at SK. F derivative SK. Now from here, I move EK squared to the left side, so EK over EK squared is equal to 1/2 F SK. Now take absolute value. Absolute value. 1/2. 2 factorial. 2 factorial actually is 2. Okay, now take limit. Okay, take limit. K approaches infinity. Recall that I assume xk approaches 0, and psi this point is between xk and 0, so psi also approaches 0. Therefore, this whole thing approaches this 0. F 0. Okay, if we further assume derivative of R and derivative of function f at R is non-zero, then this number and also second derivative non-zero, then this number is C. C is greater than 0. So under this assumption, okay, derivative non-zero. Second derivative, if second derivative is 0, then this is a better than quadratic convergence. So actually this condition, okay, is less important. If this guy is 0, then that means that the limit is 0. Limit is 0, better than quadratic convergence. So important is we assume this non-zero. When this non-zero, then we get this C greater than or equal to 0. So at least quadratic convergence. Yeah. So this is the proof of this equation, this limit. Yeah. So Newton's method is a quadratic method, converge very fast. But Newton's method, in summary, is only a method in theory, not in practice.